So you people know what is a transmission line as defined in the earlier classes. It is a pair of wires on which are all called as conductors and carries current in the opposite direction. And a transmission line is always analyzed either by the solutions of Maxwell's field equations or by the method of distributed circuit theory. And Maxwell's field equations you have studied in electromagnetic theory in the previous semesters. That is in the fourth semester, I think. You have studied the electromagnetic field theory. So the same Maxwell's field equations are utilized here also. And that's the purpose why people were informed to just have a revision about the electromagnetic theory during your initial days of the MWA class. Okay, so coming to the conclusion that you people know about the Maxwell's field equation, let us start with derivation. There are two methods how we can analyze a transmission line. One is by means of Maxwell's field equation, or is the other one would be by means of distributed circuit theory. What is the major difference between these two is, if we are trying to analyze the transmission line by means of Maxwell's equation, it involves three space variables in addition to the time variable. But if you go by the method as distributed circuit method, it involves only one space variable in addition to the time variable. Okay, so these are the differences when we try to analyze the transmission lines by means of these two methods, that is Maxwell's field equation method, or the second method is distributed circuit theory method. In Maxwell's equation, three space variables are considered in addition to the time variable, but in distributed circuit method, one space variable is considered in addition to the time variable. Here we are making use of the distributed circuit method. The distributed circuit method is used to analyze a transmission line when it can be analyzed in terms of voltage, current, impedance and power along the line. Okay. And next, based on the uniformity distributed circuit theory, the schematic of the conventional two-conductor transmission line with constant parameters R, L, G and C is considered, where R is resistance, L is inductance, G is transconductance and C is capacitance. Okay. In this method, that is in this derivation, we are making use of the distributed circuit method to analyze the transmission line. So in this distributed circuit method, the important terms or the important parameters that we are going to analyze are voltage, current, impedance, that is Z0 is impedance, and power along the transmission line. So based on this uniformity distribution circuit theory, we will write the schematic of the conventional two-conductor transmission lines, where we consider with constant parameters, that is R, L, G and C. So this is the circuit diagram. This circuit which we are considering as a transmission line. So this is the elementary section of a transmission line. So a transmission line should have a generator where it is the input, and it should always have a load where it is the output. Okay, the generator end is the end where the input is given, and the load end is the end where the output is taken. And we can also analyze the impedance and admittance parameters in terms of generator and load. So at the generator we analyze the impedance, and at the load we get the admittance. Okay, so let us consider this circuitry or its transmission line. And for this derivation, you are basically considering the parameters R, L, G and C. Okay. So when you want to analyze the transmission line, here basically we take the component of it. So in this circuit, you can see that we have the generator, we have the resistor, inductor and the transconductance G, and the voltage applied across the input is V of Z, T. And as I told you, as we are following with the distributed circuit theory system, we are considering a elemental factor of it. So R is expressed as R delta Z, and L inductance as L delta Z, and G transconductance as G delta Z. And the input voltage which is generated by the generator is V Z comma T, V of Z comma T. So this is in accordance the input of the transmission line. And the load, whenever there is a reflection, we consider it as the output terminal. And in this transmission line, let us consider for the second loop. This is first loop, this is second loop. Here, the capacitance comes into picture, where the capacitance is expressed as C into delta Z. And once again, a current is induced in the transmission line. So the current which is induced is considered as I of Z comma T. Okay. And next, once again, in the secondary part of the circuit also, we have the component resistor and the inductor. So it is R delta Z and L delta Z. And the current is IG. Okay. And here in the next loop, the voltage changes into V of Z plus delta Z comma T. And finally, at the output, once again, there is a resistor which is connected, and once again the current is forwarded. Now at the third loop, this is the loop 3, we have the current parameter IC, and which is expressed as I of Z plus delta Z comma T. As we are taking the parameters in terms of time variance, because the power has to transmit from one terminal to the other third terminal in the transmission line. That's why we take the component Z plus delta Z in terms of T. Means we take it, we also consider the time as the important parameter. Okay, so this is the example of a elementary transmission line for which we are going to analyze the equations of voltage and current for the circuitry. Okay, so you people know about the Kirchhoff's voltage law, which you have studied since your 8th standard or 9th standard. You have studied the KCL and the KVL equations. So we are considering applying the KVL equations, or as by applying the Kirchhoff's voltage law, the summation of the voltage drops around the central loop. That is, this is the central loop what we are considering. So when we apply the KVL equations for the central loop, the output value what we obtain, or the output equation which we obtain, is V of Z comma T is equal to I of Z comma T into R delta Z plus L delta Z. As the inductance, it is differential of it. So I Z comma T, V of Z comma T, dou V into ZT by dZ into delta Z. Okay. So this is by applying the KVL equations for the center loop. And by arranging the expression, these are the steps where each step is shown in individual slide. Okay. These are the basic analysis what we are doing, and this is derivation. And next, after that, by rearranging the above equation and dividing it by AZ, and then omitting the argument, that is Z of T, we obtain the next equation, that is minus dou V by dou Z is equal to Ri plus L into dou I by dou T. That is, we are analyzing the output parameter in terms of resistance and inductance. Okay. And next, we are applying the Kirchhoff's voltage law. So the summation of currents at point B, that is, this is point B in the circuitry, this is point A, and now we are analyzing the current at point B. So we get the equation minus dou I by dou Z is equal to GV plus C or C into dou V by dou T. And next, and all these transmission line equations are applicable to the general transit solutions, which you have studied in the earlier semesters, that is in your electromagnetic theory. So the instantaneous line voltage and current is always expressed as V of Z comma T is equal to RE V of Z into e to the power j omega t. And in same way, the current equations can be written as I of z comma t is equal to Re into I of z e to the power j omega t. Always there are the few imaginary values which we take into consideration. That's why we are expressing the equations for voltage and current as imaginary value. That is Re into V of z into e to the power j omega t, and I of z comma t is equal to Re into I z to the power z into e to the power j omega t. Next further, whenever we want to get the propagation constant, here the propagation constant, yes, alpha is equal gamma is equal to alpha plus j beta. So here also you can see we have the real component and the imaginary component. Okay, so when we want to analyze the propagation constant, we have gamma is equal to alpha plus j beta. And whenever we substitute the value of j omega and divide each by j omega, then finally we have the transmission lines equations in the phasor form, which can be analyzed in the frequency domain. So we have the four set of equations, that is dv by dz is equal to minus zi, and di by dz is equal to minus yv. That is, we are getting the output in terms of characteristic impedance. This is admittance as it is the output, analyze the output. In same way, d square v by dz square is equal to gamma square into v, and d square I by dz square is equal to gamma square I. Okay, so here we are trying to get the output in terms of current and voltage. So the current is minus Zi, because as the output is analyzed at the as a current parameter, it is minus Zi, where it is admittance in relevance to admittance, and voltage is minus Yv. And now what we can do is, let us substitute that. Already these things you know in your network theory also you have studied about this equations. That is, the impedance Z is equal to R plus J omega L, and the admittance Y is equal to G plus J omega L. And whenever we want to give the propagation constant, that is gamma, it is root of Z into Y. Okay, that is alpha beta J beta. So by considering this, we can analyze the transmission lines for a lossless line. So for a lossless line, one condition is always the value of R and G is equal to 0. So whenever the value of R, that is resistance and transconductance, is equal to 0, then the final equations for the voltage and current in a transmission line is expressed as dV by dz is equal to minus j omega L into I, and di by dz is equal to minus j omega C into V, and d square V by dz square is equal to minus omega square LCV, and d square I by dz square is equal to minus omega square LC into I. So here finally what you analyze is, it's the parameter, that is voltage and current parameters, is always analyzed. Okay, so finally we have the solutions for transmission line in terms of voltage and current, where voltage is expressed as V is equal to V plus e to the power minus gamma z plus V minus e to the power gamma z. Okay, so we are trying to express the output in terms of phase velocity and in terms of voltage, which is expressed in terms of phase velocity. So finally we have V is equal to output voltage, V is equal to V plus e to the power minus alpha z e to the power minus j beta z, because we know gamma is equal to alpha plus j beta. That's why you get this equation like this. And V minus e alpha to the power alpha z e to the power j beta z. And the same way we can also express the output current in terms of voltage, where it is that is admittance, that is y naught. So as we take the admittance parameters, almost it reflects the same, but only this is minus. Okay. So this is the one possible solutions for transmission lines in terms of voltage and current. And in the examination, this steps what I has been explained now, this should be asked for 8 marks. Derive the equations, transmission line equations for a network, for a microwave transmission line, or is for a transmission line. Okay. So these are the steps what you are supposed to write. First of all, you write the circuit diagram and you analyze, you just need to write the preamble for this, what are the methods that you are using, and write the circuit diagram and write the equations what has been explained until now. Okay, so these are the derivations, these are the equations using which we can analyze the voltage and current in a transmission line. Further, there are also few of the things which we can analyze in a microwave signal, or as for a signal which is traveling at microwave frequency. So at microwave frequency, we can observe that always the resistance value R is very much less than omega L, and the value G is very much less than omega C. Okay. So by this, considering these conditions, the binomial expansion or the propagation constant gamma can be expressed as gamma is equal to root of R plus j omega L into G plus j omega C. This is these are one of the few of the important equations, because sometimes they ask these questions for just 5 marks. Write the binomial expansion expressions for phase velocity, or as propagation of the signal, phase velocity. So during that time you are supposed to write this. Okay. So at microwave frequencies, it is observed that always the value of resistance is very much less than omega L, and the transconductance value is always G is very much less than omega C. And by using this, we can express the constant, phase constant, gamma is equal to root of R plus j omega L. That is, gamma is equal to root of R into Z, right? So by that condition, we can write R is equal to root of R plus j omega L into G plus j omega C. So further substituting with the basic equations, we can also get gamma is equal to root of j omega square LC into root of 1 plus R by j omega L plus 1 by G divided by j omega C. So further by substitution, once again we arrive at the final equation where gamma is equal to 1 by 2 R into root of C by L plus G into root of L by C plus j omega into root of LC. Okay, so here as alpha is equal gamma is equal to alpha plus j beta, we can write that the first parameter alpha, this is alpha. Okay, so the alpha propagation constant alpha is equal to 1 by 2 root into R into root of C by L plus G into root of L by C, whereas the value beta is equal to omega into root of LC. Okay, so these are the equations for propagation constants gamma, and these are the expressions for alpha and beta, because you have few of the numericals which you should solve using this equation. Okay, so please you should remember these equations to solve the numericals, because in part B of module 1 questions you'll have these derivations and you'll have one numerical which you have to solve. Next, how do you find the characteristic impedance Z0 and the phase velocity Vp? There is characteristic Z0. This is also one of the equation which you have to derive. As we all know, characteristic impedance Z0 is equal to root of R by L. So it is R plus j omega L divided by G plus j omega C. So further, upon substitution by the basic equations, we get the final value of phase velocity z0 is equal to root of L by C. So now Vp is equal to omega by beta, which is 1 by root of L into C. Okay. So phase velocity in terms of cascade impedance can be obtained as Vp is equal to omega by beta, which is 1 by root LC. Okay. Any clarifications with this? Because they can either ask the first part of the derivation or else they can also ask only the second part of the derivation. Means two questions can be expected from this topic which has been explained. That is, derive the transmission line equations for a elementary section of a transmission line, for which you are supposed to write the answers up till this. These are the equations of voltage and current for a transmission line, two-wire transmission line. And further, there will be a short answer question where they ask you to derive the expression for propagation constant along with basic equations for R and L. So we have these equations. Okay. So this is one of the important derivation in your module 1. And further, no derivations are there, only the theoretical concepts of it.